Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the vast emptiness between stars, where ancient travelers drift in silence for millions of years. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. In the darkness between stars, where no light has traveled for billions of years, a mountain of ice and rock drifts through the absolute cold. This is 3I/Atlas, not its given name, but the designation astronomers use to track its slow passage through our corner of the galaxy. The 3I marks it as the third interstellar object detected entering our solar system, though countless others have passed unnoticed through the centuries, their presence known only to the gravitational mathematics that govern celestial motion. The comet moves at nearly 60,000 miles per hour relative to our Sun. Yet, in the scale of interstellar distances, this represents little more than the pace at which fingernails grow on Earth. The visitor carries within its frozen heart the original materials of stellar formation, water ice mixed with carbon monoxide, carbon dioxide, and traces of methane, all compressed and preserved in the deep cold for 4.5 billion years. These substances froze when our galaxy was younger, when the spiral arm that contains our solar system held different stars in different positions, when the Orion arm itself occupied a different region of galactic space. The comet remembers temperatures that have not existed in our local region of space since before Earth formed its first solid crust, before the Moon learned its current distance from our planet, before the Sun settled into the steady nuclear burning that has continued unchanged for nearly 5 billion years. Scientists estimate the nucleus measures perhaps 2 miles across at its widest point, though its exact dimensions remain uncertain in the darkness that conceals its true shape. This makes it smaller than most asteroids that occasionally approach Earth, yet it carries enough frozen material to create spectacular displays when solar radiation begins its patient work of transformation. The surface reflects only 4% of the light that reaches it, darker than charcoal, darker than the blackest earthly soil, darker than volcanic glass cooled in the depths of ocean trenches. This darkness absorbs heat that will not reach the comet's interior for centuries, creating temperature gradients so extreme that the outer layers might sublimate into space while the core remains locked in primordial ice. In its present location, far beyond the orbit of Pluto, far beyond the heliopause where solar wind meets interstellar medium, the comet experiences temperatures near absolute zero, negative 450 degrees Fahrenheit, cold enough that nitrogen itself would freeze solid, cold enough that oxygen becomes a crystalline substance harder than most earthly metals. At these temperatures, molecular motion slows to nearly nothing. Ice becomes harder than granite, more durable than diamond. The boundary between solid and gas ceases to exist in any form familiar to terrestrial experience, replaced by quantum mechanical processes that operate according to probability rather than classical physics. Only the quantum movement of subatomic particles continues unchanged at these temperatures, maintaining the fundamental forces that hold matter together across the universe's longest scales. Electrons still orbit atomic nuclei, though their energy states drop to the lowest possible levels permitted by quantum mechanics. Nuclear forces continue to bind protons and neutrons together in the comet's rocky components, unchanged by the cosmic cold that has preserved this visitor since the early epochs of galactic formation. The comet's trajectory carries the weight of gravitational interactions with stars that burned out before our Sun ignited. stars whose names exist only in the radio emissions they produced during their final collapse into white dwarfs or neutron stars. Its orbital path remembers encounters with stellar remnants, brown dwarfs that never achieved sustained fusion, and gas giants orbiting other stars in distant planetary systems, a navigation system written in celestial mechanics rather than memory, encoded in momentum and angular velocity rather than conscious recall. Each gravitational encounter over the millennia has altered its course by fractions of degrees, changes so small they require thousands of years to become apparent, yet significant enough to determine which star system the comet approaches next, which planets it might influence, which observers might detect its passage through their local region of space. From Earth's perspective, even through the most powerful telescopes, the visitor appears as little more than a faint smudge of light, indistinguishable from background galaxies except for its slow motion against the stellar backdrop. Professional astronomers require multiple nights of observation to confirm its movement. Measuring position changes smaller than the apparent width of a human hair viewed from across a football field. The comet's reflected sunlight, already feeble at such distances, must compete with the glow of zodiacal dust that fills the plane of our solar system, atmospheric turbulence that distorts all ground-based observations, and the light pollution that surrounds most observatories on Earth. Yet, within this seemingly insignificant speck of reflected light lies a record of conditions that existed when the Milky Way galaxy contained half its current complement of heavy elements. The frozen gases trapped in the comet's interior represent samples of the interstellar medium from an era when carbon, oxygen, and silicon were still rare products of stellar fusion, before generations of dying stars had enriched the galaxy with the materials necessary for rocky planets and organic chemistry. The water molecules locked in the comet's ice formed in the hearts of stars that completed their fusion cycles billions of years ago. Stars that created hydrogen and oxygen in the nuclear fires of their cores before expelling these materials into space through stellar winds and supernova explosions. The mystery that surrounds this visitor extends beyond its composition to its origin. Astronomers cannot determine with certainty which star system first captured the comet in its gravitational embrace, which planetary system it might have orbited before beginning its interstellar journey. The gravitational influences that shaped its current trajectory have erased most evidence of its previous orbital history, leaving only mathematical possibilities and statistical probabilities. Some models suggest it originated in a system similar to our own, with gas giants capable of ejecting comets into interstellar trajectories. Other calculations point toward red dwarf stars, smaller and cooler than our Sun, capable of maintaining planetary systems for trillions of years, long enough for countless gravitational perturbations to eventually release cometary materials into galactic space. As the comet continues its approach toward our Sun, still months away from any visible activity, still years away from its closest approach to our star, it maintains the perfect preservation that only interstellar space can provide. No atmosphere disturbs its surface with weather or erosion. No magnetic field channels charged particles across its frozen landscape, creating auroras or electrical phenomena. No geological processes reshape its terrain through tectonics or volcanic activity. No biological processes alter its chemical composition through metabolism or decay. It remains exactly as it was when it first condensed from the collapse of its birth nebula, a time capsule moving at cosmic velocities through the patient darkness, carrying its ancient cargo toward an appointment with our star that was determined long before Earth's first continents emerged from primordial oceans, long before the first organic molecules achieved the complexity necessary for self-replication, long before consciousness emerged anywhere in our local region of the galaxy. The gravitational reach of our Sun extends far beyond the visible planets, far beyond the scattered disk of distant Kuiper Belt objects, stretching across nearly 2 light-years of space in a sphere of influence that encompasses thousands of times the distance from Earth to Pluto. Within this vast domain, known to astronomers as the Hill sphere, the Sun's gravity operates like a cosmic tide, pulling gently on every particle of dust, every fragment of ice, every wandering asteroid that passes through the outer boundaries of our stellar neighborhood. The comet first encounters these gravitational whispers at distances so great that our Sun appears no brighter than any other star in the constellation patterns visible from Earth, indistinguishable from the thousands of similar points of light that fill the night sky. At such distances, roughly 50,000 astronomical units from our star, the Sun's gravitational influence amounts to little more than a few millimeters per second squared. Acceleration so gentle that a feather falling in Earth's gravity would seem violent by comparison. Yet this subtle force operates continuously across millions of years, gradually bending the comet's trajectory from the straight line it followed through interstellar space toward the curved path that will eventually bring it within sight of human telescopes. The mathematics of orbital mechanics dictate that this gentle deflection will ultimately accelerate the visitor to speeds exceeding 100,000 miles per hour as it approaches the inner solar system, transforming potential energy stored in distance into kinetic energy of motion. The comet's response to solar gravity reveals the elegant relationship between mass, distance, and time that governs all celestial motion throughout the universe. Its nucleus, perhaps 10 billion tons of ice and rock compressed into a volume smaller than most earthly cities, represents a negligible fraction of our Sun's mass, roughly equivalent to comparing a grain of sand to a bowling ball. Yet the gravitational interaction between these two objects follows the same mathematical principles that govern binary stars: galactic rotation, and the expansion of the universe itself. Newton's law of universal gravitation, formulated 3 centuries ago to explain the motion of planets and moons, applies with perfect accuracy to this visitor from interstellar space, demonstrating the fundamental unity of physical laws across all scales of cosmic distance and time. As the comet begins its long fall toward our star, accelerating by imperceptible amounts each day, it carries momentum inherited from its previous orbital history, the accumulated gravitational influences of every stellar encounter over the past several million years. This momentum represents a form of cosmic memory, encoding the gravitational signatures of stars that may have exploded as supernovae, collapsed into neutron stars, or expanded into red giants long after their brief encounter with this wandering visitor. The momentum cannot be destroyed or created, only redirected according to the conservation laws that govern all motion in the universe, from subatomic particles to galactic clusters. The sum of kinetic and potential energy in the comet's trajectory remains constant throughout its journey, transforming gradually from the potential energy of distance into the kinetic energy of velocity as solar gravity draws the visitor inward. This energy balance, known as conservation of mechanical energy, ensures that the comet will achieve its maximum velocity at perihelion, when it passes closest to our star, before gradually slowing again as it recedes into the outer solar system. The total energy of the system, Sun plus comet, remains unchanged by their gravitational interaction, distributed between kinetic motion and gravitational potential in precise mathematical proportion. The precision required to predict the comet's future path challenges the limits of computational astronomy and reveals the fundamental complexity of gravitational systems containing multiple massive objects. Astronomers must account not only for the Sun's gravitational influence, but also for the smaller perturbations caused by Jupiter, Saturn, and the other gas giants, each of which will slightly modify the comet's trajectory as it approaches the inner solar system. These calculations extend across millions of orbital positions, each dependent on the accuracy of the previous computation, creating mathematical models that amplify small errors into large uncertainties over time, scales longer than human civilization. Jupiter's gravitational influence alone, though much weaker than the Sun's at the comet's current distance, will eventually deflect the visitor's path by several degrees during its closest approach to the giant planet. Saturn's rings and moons add their own subtle perturbations, as do the smaller influences of Uranus, Neptune, and even the rocky planets of the inner solar system. The cumulative effect of these interactions creates what mathematicians call a chaotic system, one whose long-term behavior becomes impossible to predict with certainty. Despite following perfectly deterministic physical laws, the mystery of the comet's exact arrival time illustrates the fundamental limits of predictive precision in chaotic systems, a phenomenon discovered only in the 20th century despite governing celestial mechanics since the formation of the solar system. While astronomers can calculate the comet's approximate position months or years in advance, the exact moment of perihelion, its closest approach to the Sun, remains uncertain by several days or weeks. This uncertainty does not result from inadequate measurements or computational limitations, but from the inherent sensitivity of gravitational systems to initial conditions, a mathematical property that makes long-term prediction impossible, even with perfect knowledge of current positions and velocities. The three-body problem, as mathematicians call the interaction between Sun, comet, and Jupiter, has no general analytical solution despite 2 centuries of mathematical investigation by some of history's greatest minds. Henri Poincaré demonstrated in the 19th century that such systems exhibit sensitive dependence on initial conditions, meaning that tiny differences in starting positions or velocities can lead to dramatically different outcomes over time. The comet's trajectory, determined by the positions and velocities of dozens of solar system objects, represents a solution to an even more complex, many-body problem that can only be approximated through numerical computation. Among the ironies of celestial mechanics, the comet's acceleration toward our Sun occurs so gradually that human observers cannot detect its increasing speed without months of careful measurement and mathematical analysis. The visitor appears to move with the steady patience of geological time, crossing vast regions of space at velocities that would circumnavigate Earth in minutes, yet requiring years to travel from the orbit of Neptune to the orbit of Mars. Only when compared to the fixed background stars does its motion become apparent, a demonstration that the perception of speed depends entirely on the observer's frame of reference and chosen timescale. The comet's journey inward occurs during a period of relative solar quiet, when our star maintains the steady nuclear burning that has characterized its middle age for billions of years. Solar output varies by less than 0.1% over periods of decades, providing a stable gravitational and radiative environment for the comet's approach. Had this visitor arrived during the Sun's more active youth 4 billion years ago, when stellar winds were stronger and solar output less predictable, its trajectory and ultimate fate might have differed significantly from the path astronomers now observe and attempt to predict. The gravitational acceleration experienced by the comet follows an inverse square relationship with distance, doubling in strength each time the visitor halves its distance from the Sun, quadrupling when the distance decreases by half again. This mathematical relationship, discovered by Newton and verified by centuries of astronomical observation, ensures that most of the comet's acceleration will occur during the final months of its inward journey, when it passes through the orbital distances of the outer planets and begins to experience the full gravitational pull of our star. The gentle tug that now influences its motion will eventually become a powerful acceleration capable of deflecting the visitor's path by many degrees, potentially altering its trajectory enough to determine whether it remains bound to our solar system or escapes back into interstellar space. As the comet continues its slow approach through the darkness beyond Neptune's orbit, still invisible to most earthly telescopes, it maintains the pristine surface conditions that have preserved its original composition for billions of years. No solar heating disturbs the equilibrium between its frozen components. No sublimation removes material from its nucleus, no coma or tail betrays its presence to observers on Earth. It remains hidden in the cosmic darkness, a patient mountain of ancient ice falling slowly toward the light and warmth that will eventually transform its appearance beyond recognition, revealing secrets locked in ice since the formation of our galaxy's spiral arms. Beyond the orbit of Neptune, where sunlight arrives 800 times dimmer than it reaches Earth, the comet crosses into a realm where ice behaves like metal and silence reigns absolute. Here, at 30 astronomical units from our star, the visitor encounters the first subtle changes in solar radiation pressure, not enough to warm its surface by even a single degree, but sufficient to begin the slow process of gravitational capture that will define its future trajectory. The boundary between interstellar space and solar influence remains invisible, unmarked by any physical barrier, yet the comet's passage across this threshold marks the beginning of its transformation from wandering exile to temporary member of our planetary family. The outer solar system through which the comet now travels represents a frontier zone where the sun's authority gradually diminishes until it becomes indistinguishable from the gravitational background of nearby stars. Pluto, when positioned at its farthest point from the sun, receives only 1/1600th of the solar energy that warms Earth's surface. At the comet's current distance, solar radiation provides barely enough energy to power a small LED light bulb across the entire surface of its nucleus. Yet even this feeble illumination begins to interact with the visitor's ancient surface chemistry, initiating molecular processes that have remained dormant for millions of years. The comet's nucleus rotates slowly as it travels, completing one full turn roughly every 18 hours, a rotation period that reflects the accumulated angular momentum from countless gravitational encounters during its interstellar journey. This spin rate, faster than Earth's rotation, yet slower than most asteroids, suggests the visitor experienced relatively gentle interactions during its formation and subsequent travels through galactic space. Had it undergone violent collisions or close stellar encounters, its rotation would likely be either much faster or tidally locked, with one hemisphere permanently facing the direction of travel. As the comet spins through the outer darkness, different regions of its surface experience the faint touch of solar radiation for the first time in millions of years. The temperature difference between day and night sides amounts to only a few degrees at these distances. Yet even this minimal variation begins to create thermal stresses within the surface layers. Ice that has remained stable since the comet's formation starts to experience the first hints of structural change, though any visible effects remain months or years in the future. The mystery of the comet's exact composition deepens as astronomers attempt to analyze the faint reflected light that reaches Earth-based telescopes. Spectroscopic observations reveal the presence of water ice mixed with darker organic compounds, but the precise ratios and molecular structures remain hidden beneath the visitor's extremely dark surface. The comet reflects so little sunlight that astronomers must integrate photons across entire nights of observation to gather enough signal for meaningful analysis, like trying to study a piece of charcoal by candlelight from across a football stadium. Among the subtle ironies of outer solar system dynamics, the comet's approach occurs during a period when Neptune occupies the opposite side of its orbit from the visitor's trajectory. Had the timing been different by merely a few years, the ice giant's gravity might have deflected the comet onto a significantly different path, potentially sending it into the inner solar system decades earlier or later. The gravitational influence of the outer planets extends across vast distances, creating a complex web of orbital resonances and perturbations that can dramatically alter the fate of small bodies passing through their domains. The comet's surface composition reflects the primordial chemistry of its birth nebula, when heavy elements comprised a much smaller fraction of the interstellar medium than they do today. Carbon, nitrogen, and oxygen, the building blocks of organic chemistry, existed primarily in simple molecular forms: carbon monoxide, nitrogen gas, and water vapor, the complex organic molecules that characterize life on Earth had not yet formed in significant quantities anywhere in the galaxy, making the comet's interior a repository of pre-biological chemistry from an era when the universe was chemically simpler and less diverse. Embedded within the comet's ice lie microscopic grains of stellar dust, the remnants of supernovae and stellar winds that enrich the interstellar medium with heavy elements during the galaxy's youth. These dust particles, smaller than bacteria, yet older than our solar system, carry isotopic signatures that reveal their origins in specific types of stars, red giants that expelled their outer layers through stellar winds, massive stars that exploded as supernovae, and perhaps even exotic objects like neutron stars or white dwarfs that contributed rare elements through unique nuclear processes. The visitor's trajectory through the outer solar system follows a hyperbolic path that curves gradually inward under the influence of solar gravity. Unlike the elliptical orbits of planets and most comets, this hyperbolic trajectory indicates that the visitor carries too much kinetic energy to remain permanently bound to our solar system. After its close approach to the Sun, it will use the gravitational energy gained during its inward journey to escape back into interstellar space, carrying with it a slightly altered velocity and trajectory that will determine its next stellar destination millions of years in the future. The comet's passage through this region of space occurs in virtual isolation, separated from the nearest known objects by millions of miles of vacuum. No atmosphere cushions its journey. No magnetic field protects it from cosmic radiation. No gravitational companions modify its rotation or create tidal forces across its surface. It travels alone through the cosmic darkness, accompanied only by the ancient ice and rock that have formed its unchanging bulk since the era of galactic formation, maintaining perfect preservation in the natural refrigerator of interstellar space. Temperature measurements of the comet's surface, gathered through infrared observations that detect the faint heat radiated by any object above absolute zero, reveal a nearly uniform surface temperature of approximately -400 degrees Fahrenheit. At these temperatures, the visitor's surface ice behaves more like rock than any terrestrial conception of frozen water. Crystalline structures lock water molecules into rigid lattices harder than steel, while trace amounts of other frozen gases create a complex mixture of ices with different melting points, sublimation rates, and thermal properties. The comet's approach velocity relative to our solar system, nearly 20 miles per second, indicates it originated from a stellar region moving with different galactic orbital characteristics than our local stellar neighborhood. This velocity difference, small by galactic standards, suggests the visitor traveled for millions of years through interstellar space before encountering our Sun's gravitational influence. During this journey, it experienced the gentle pressure of starlight from distant suns, the gravitational tugs of passing stars, and perhaps even the shock waves from nearby supernovae, all contributing minor influences to its eventual arrival in our cosmic vicinity. As the comet continues its slow approach toward the inner solar system, still months away from any dramatic changes in appearance or behavior, it maintains the perfect equilibrium between its internal structure and the external environment of deep space. No geological processes reshape its surface. No atmospheric phenomena disturb its ancient landscape. No biological processes alter its chemical composition. It remains exactly as it formed billions of years ago, a pristine sample of conditions that existed when our galaxy was young and chemically simple, carrying this precious cargo toward an inevitable encounter with solar radiation that will reveal its secrets to human observation. Jupiter's immense gravitational field reaches across hundreds of millions of miles, creating invisible corridors of influence that shape the trajectories of countless small bodies throughout the outer solar system. The gas giant's mass, more than twice that of all other planets combined, generates gravitational effects detectable at distances greater than the orbit of Saturn, making it the primary architect of cometary paths for visitors approaching from interstellar space as the comet continues its inward journey. Still beyond the orbit of Uranus, it begins to feel the first whispers of Jupiter's gravitational assistance, a phenomenon that will ultimately determine whether the visitor gains enough velocity to escape our solar system or becomes permanently captured in a new orbital pattern around our Sun. The mathematics of gravitational assists, first understood through the space missions of the 20th century, reveal how massive planets can transfer orbital energy to smaller objects without losing any significant momentum themselves. Jupiter's orbital motion around the Sun carries kinetic energy equivalent to millions of hydrogen bombs exploding every second. Yet, this enormous reservoir of energy experiences no measurable depletion when shared with passing comets and asteroids. The gas giant acts like a cosmic slingshot, using its gravitational field to accelerate or decelerate visitors depending on their approach trajectory and the precise timing of their closest encounter. For the approaching comet, Jupiter's gravitational influence manifests as a gradual deflection of its trajectory, bending the visitor's path by fractions of degrees over periods of months. This deflection occurs according to the inverse square law that governs all gravitational interactions. The closer the comet approaches to Jupiter, the stronger the gravitational acceleration becomes, following mathematical principles that remain constant throughout the universe. The precise geometry of this gravitational dance depends on factors determined millions of years ago: the comet's original velocity vector, its angle of approach to our solar system, and the current positions of Jupiter and the other outer planets in their eternal orbital choreography. The timing of the comet's approach relative to Jupiter's position represents one of countless cosmic coincidences that influence the fate of interstellar visitors. Had the comet arrived merely a few years earlier or later, Jupiter might have occupied a different position in its 12-year orbit around the Sun, potentially altering the visitor's trajectory by thousands of miles at perihelion. These timing dependencies illustrate the chaotic nature of multi-body gravitational systems, where small changes in initial conditions can produce dramatically different outcomes over astronomical timescales. Jupiter's four largest moons, Io, Europa, Ganymede, and Callisto, add their own subtle gravitational perturbations to the comet's trajectory. Though their combined mass amounts to less than 1% of Jupiter's total, these Galilean satellites orbit their parent planet in a complex resonance pattern that has remained stable for billions of years. Yet their gravitational signatures create minor variations in the gravitational field that the comet will experience during its closest approach to the Jovian system. The mathematical complexity of calculating these multi-body interactions requires sophisticated computer models that integrate millions of orbital positions to predict the visitor's future path with reasonable accuracy. The mystery of predicting exactly how Jupiter's gravity will affect the comet illustrates the fundamental limits of deterministic chaos in astronomical systems. While the basic gravitational physics remains perfectly understood, the extreme sensitivity of the comet's trajectory to small perturbations makes long-term prediction increasingly uncertain as the time horizon extends beyond several orbital periods. Astronomers can calculate the general region where the comet will pass closest to Jupiter, but the exact distance and timing of this encounter remain uncertain by margins that could significantly influence the visitor's ultimate fate. Among the ironies of gravitational mechanics, Jupiter's influence on the comet begins months before their closest approach, gradually accelerating the visitor toward a velocity that will eventually carry it past the gas giant in a matter of hours. The comet spends more time approaching Jupiter than it does in the planet's immediate vicinity, yet the strongest gravitational effects occur during the brief period of closest approach, when the visitor experiences acceleration forces thousands of times stronger than those it encounters in the outer solar system. This concentration of gravitational influence into short time periods characterizes all close encounters between astronomical objects, from binary star systems to galactic collisions. The comet's trajectory past Jupiter follows a hyperbolic path relative to the gas giant, curving around the planet's gravitational field like a stone thrown past a massive magnet. The exact shape of this hyperbola depends on the comet's approach velocity and the minimum distance achieved during closest approach, parameters that determine how much kinetic energy the visitor gains or loses during its encounter with Jupiter's gravitational field. If the geometry proves favorable, the comet could gain enough velocity to ensure its eventual escape from our solar system. If unfavorable, it might lose enough energy to become gravitationally bound to the Sun for future orbital periods. The gravitational assist provided by Jupiter operates through the same physical principles that govern the orbital mechanics of artificial satellites and interplanetary spacecraft. The comet effectively borrows a tiny fraction of Jupiter's orbital momentum, gaining velocity in the direction of the gas giant's motion around the Sun, while Jupiter experiences an infinitesimally small decrease in its own orbital velocity. This exchange of momentum conserves the total energy and angular momentum of the Jupiter comet system, demonstrating the universal applicability of conservation laws even in the most complex gravitational interactions. As the comet approaches the region of space where Jupiter's gravitational influence becomes dominant over that of more distant objects, its trajectory begins to curve more sharply inward toward the inner solar system. The visitor's velocity relative to the Sun increases steadily as gravitational potential energy converts to kinetic energy, following the same energy conservation principles that govern all orbital motion. This acceleration occurs so gradually that human observers cannot detect velocity changes without precise measurements extended over weeks or months of observation. Yet, the cumulative effect will ultimately double or triple the comet's speed by the time it reaches the inner solar system. The comet's passage through Jupiter's gravitational domain occurs during a period when the gas giant maintains its usual complement of atmospheric storms, including the Great Red Spot, a hurricane-like vortex larger than Earth that has persisted for centuries. These atmospheric phenomena have no direct influence on the comet's trajectory, yet they serve as reminders of the dynamic processes that occur within planetary systems throughout the galaxy. Jupiter's internal heat source, generated by the slow gravitational compression of its massive atmosphere, radiates more energy into space than the planet receives from solar radiation, creating weather patterns that dwarf any meteorological phenomena on Earth. The visitor's approach trajectory carries it past Jupiter's magnetosphere, a region of charged particles trapped by the gas giant's powerful magnetic field extending millions of miles into space. This magnetosphere, generated by electric currents flowing within Jupiter's metallic hydrogen core, creates radiation environments intense enough to damage spacecraft electronics and alter the surface chemistry of nearby moons. The comet's passage through this region exposes its ancient surface to high-energy particles that have remained trapped in Jupiter's magnetic field for decades, potentially triggering chemical reactions in the visitor's surface ices that have not occurred since its formation in the interstellar medium. The gravitational focusing effect created by Jupiter's mass concentrates the trajectories of incoming objects into preferred approach corridors, making the gas giant both a protector and a threat to the inner planets. Objects deflected by Jupiter's gravity may be sent into orbits that carry them toward Mars, Earth, and Venus, while others receive enough velocity to escape the solar system entirely. This dual role as cosmic guardian and potential threat illustrates the complex relationship between gravitational dynamics and the long-term stability of planetary systems throughout the galaxy. As the comet continues its approach toward Jupiter's gravitational sphere of influence, it maintains the pristine surface conditions that have preserved its original composition since formation. The visitor's dark nucleus reflects so little sunlight that it remains invisible to most telescopes, detectable only through the gravitational perturbations it creates in the orbits of other objects or through the faint infrared radiation emitted by its surface. This thermal emission generated by the slow radioactive decay of elements within the comet's rocky components, provides one of the few observational signatures that allow astronomers to track the visitor's position and predict its future trajectory through the complex gravitational environment of the outer solar system. Solar radiation begins its patient work as the comet crosses the orbital distance of Saturn, still 28 astronomical units from our star, yet finally receiving enough energy to initiate the first subtle changes in its ancient surface chemistry. At this distance, sunlight arrives with barely 1% of the intensity that illuminates Earth. Yet, this feeble radiation carries sufficient energy to break the weakest molecular bonds in the comet's surface ices. Water molecules that have remained locked in crystalline structures for billions of years begin to vibrate with increasing amplitude as solar photons transfer their energy to the frozen matrix, creating the first microscopic cracks in ice harder than granite. The process of sublimation, the direct transition from solid to gas without passing through a liquid phase, begins almost imperceptibly across the comet's surface as solar heating penetrates the outermost layers of ancient ice. Individual water molecules escape from crystal lattices at rates measured in billions of molecules per square centimeter per second. Yet these escaping gases remain invisible to human observation, creating a tenuous atmosphere around the nucleus so diffuse that it would qualify as a laboratory vacuum on Earth. The comet's weak gravitational field, roughly 1/10,000th of Earth's surface gravity, cannot retain these escaping gases, allowing them to stream freely into space at velocities approaching the speed of sound. The mystery of which surface components sublimate first reflects the complex chemistry preserved within the comet's nucleus since its formation in the protoplanetary disk of a distant star system. Water ice, the most abundant component, requires relatively high temperatures for sublimation compared to more volatile substances like carbon monoxide, carbon dioxide, and methane. These trace gases, frozen into the water ice matrix at temperatures near absolute zero, begin to escape first as solar heating creates temperature gradients within the surface layers. The resulting outgassing follows patterns determined by the original distribution of volatile materials, creating jets and streamers of gas that emerge from specific regions of the nucleus according to the ancient chemistry of stellar formation. Spectroscopic analysis of the escaping gases provides astronomers with their first direct measurements of the comet's composition, revealing isotopic ratios that encode information about conditions in the interstellar medium when the visitor formed. The ratio of heavy water to normal water, the abundance of carbon-13 relative to carbon-12, and the presence of rare isotopes like oxygen-18 create chemical fingerprints that connect the comet to specific stellar populations and galactic regions. These measurements require integration of photons across entire nights of observation, as the escaping gases produce emission lines so faint that they challenge the sensitivity limits of the world's largest telescopes. Among the subtle ironies of cometary physics, the gases that create the comet's visible coma escape from the nucleus at temperatures hundreds of degrees below the freezing point of water on Earth. The vacuum of space allows sublimation to occur at temperatures that would preserve ice indefinitely in terrestrial environments, demonstrating how the absence of atmospheric pressure fundamentally alters the behavior of familiar substances. The escaping water vapor, carbon dioxide, and other gases expand into space at supersonic velocities, creating shock waves and turbulence patterns that remain invisible except through specialized infrared and radio observations. The comet's rotation period becomes measurable for the first time as different regions of its surface warm and cool during its 18-hour spin cycle, creating periodic variations in the brightness and composition of escaping gases. This rotation reflects the accumulated angular momentum from gravitational encounters during the visitor's interstellar journey, preserving a record of forces that acted upon it millions of years ago. The axis of rotation, tilted at an unknown angle relative to the comet's orbital plane, determines which regions of the surface receive direct solar illumination and which remain in perpetual shadow during each rotation cycle. As the coma begins to form around the nucleus, extending perhaps 10,000 miles in diameter, yet containing less mass than a small asteroid, the comet's gravitational influence on its own escaping gases becomes negligible compared to the pressure exerted by solar radiation. Photons carry momentum despite having no mass, and the intense radiation pressure near the Sun can accelerate small particles to velocities exceeding those achieved by chemical rockets. This radiation pressure, combined with the solar wind, a stream of charged particles flowing outward from the Sun's corona, begins to shape the escaping gases into the characteristic structures that will eventually become visible as the comet's tail. The mystery of the comet's internal structure deepens as thermal models attempt to predict how solar heating penetrates beneath the surface layers. The visitor's extremely low density, perhaps half that of water ice, suggests a highly porous internal structure filled with voids and fractures that could significantly affect heat conduction and gas escape patterns. These internal spaces, created during the original accretion process or by subsequent impacts with interstellar debris, provide pathways for gases to migrate from the interior toward the surface, potentially creating outbursts of activity that occur hours or days after the corresponding surface regions receive solar heating. The comet's dark surface, which reflects only 4% of incident sunlight, absorbs solar energy efficiently, yet conducts heat poorly into the interior due to the insulating properties of the porous ice structure. This creates extreme temperature gradients between the illuminated surface, which may reach temperatures above -200 degrees Fahrenheit, and the interior, which remains at the same temperature it has maintained for millions of years. The boundary between these temperature regimes moves deeper into the nucleus as solar heating intensifies, creating an advancing front of sublimation that gradually works its way toward the comet's core. The formation of the coma represents the first visible sign of the comet's awakening after eons of dormancy in interstellar space. Yet this tenuous atmosphere remains invisible to unaided human vision, detectable only through sensitive photographic techniques that accumulate light over extended periods. Professional astronomical cameras, cooled to temperatures approaching absolute zero to reduce electronic noise, can barely distinguish the comet's faint glow from the background emission of zodiacal dust and distant galaxies. The visitor maintains its anonymity even as it begins the transformation that will eventually make it one of the most spectacular objects in Earth's sky. As sublimation continues across the comet's slowly rotating surface, the escaping gases carry with them microscopic dust particles embedded in the surface ice since the visitor's formation. These dust grains, smaller than the particles in cigarette smoke, yet older than our solar system, begin their own independent journeys through space, following trajectories determined by their size, composition, and the radiation pressure they experience from solar photons. The largest particles, roughly the size of sand grains, remain gravitationally bound to the comet for weeks or months, while the smallest particles escape immediately into interplanetary space, contributing to the zodiacal dust that fills the plane of our solar system. The comet's awakening occurs gradually over periods of months as its orbital velocity increases and solar heating intensifies according to the inverse square law that governs all radiation. Each day brings slightly warmer surface temperatures, slightly higher sublimation rates, and slightly more visible activity. Yet, the changes occur so slowly that human observers require sophisticated instruments to detect the increasing brightness and expanding coma. The visitor approaches its eventual spectacular display with the patience of geological time, revealing its ancient secrets one molecule at a time as solar energy unlocks chemical bonds that have remained stable since the era when our galaxy contained half its current population of heavy elements. The twin tails that will eventually stretch millions of miles across space begin their formation as a barely perceptible asymmetry in the comet's expanding coma. Invisible to human observation, yet detectable through careful analysis of the escaping gases and dust particles, solar radiation pressure, operating through the momentum carried by individual photons, pushes the smallest particles away from the Sun with accelerations that can exceed the comet's own gravitational pull by factors of hundreds or thousands. Meanwhile, the solar wind, a stream of charged particles flowing outward from our star's corona at velocities approaching 1 million miles per hour, sweeps ionized gases into distinctive patterns that follow the magnetic field lines embedded in the interplanetary medium. The dust tail forms first, composed of particles ranging in size from individual molecules to grains as large as pebbles, each following its own independent orbit around the Sun according to the laws of celestial mechanics. The smallest particles, pushed most efficiently by radiation pressure, stream away from the comet in a direction exactly opposite to the Sun, creating a straight tail that points away from our star like an arrow indicating the direction of solar radiation. Larger particles, influenced more by their own orbital momentum than by radiation pressure, curve away from the comet's nucleus in gentle arcs that trace the mathematical relationship between particle size, radiation pressure, and gravitational attraction. The ion tail develops more slowly as solar radiation ionizes the escaping gases, stripping electrons from water vapor, carbon dioxide, and other molecular species to create electrically charged particles that interact with the magnetic fields carried by the solar wind. These ionized gases follow the complex topology of interplanetary magnetic field lines, creating structures that can change dramatically within hours as the solar wind conditions vary according to the 11-year cycle of solar activity. The ion tail typically appears straighter and more dynamic than the dust tail, capable of developing kinks, disconnections, and other dramatic features as magnetic field lines reconnect and reconfigure around the comet's expanding coma. The formation of both tails requires the comet to lose millions of tons of material each day, yet this mass loss represents only a tiny fraction of the visitor's total bulk, accumulated over billions of years of patient wandering through interstellar space. Mathematical models suggest that a typical comet can survive hundreds or thousands of passages through the inner solar system before sublimation reduces its nucleus to a collection of inert, rocky fragments. The current visitor, experiencing solar heating for perhaps the first time since its formation, carries enough volatile material to maintain spectacular tail development for months as it approaches and recedes from perihelion. The mystery of predicting exact tail morphology challenges astronomers because the structures depend on solar wind conditions that vary unpredictably according to the chaotic dynamics of our star's magnetic field and coronal heating processes. Solar flares, coronal mass ejections, and other manifestations of solar activity can dramatically alter the environment through which the comet travels, creating sudden changes in tail structure that occur faster than the comet's orbital motion. These interactions between comet and solar wind provide natural laboratories for studying plasma physics under conditions impossible to reproduce in terrestrial experiments. Among the subtle ironies of cometary tail formation, the spectacular structures that captivate human observers consist primarily of vacuum by terrestrial standards, containing densities of matter millions of times lower than Earth's atmosphere at sea level. The tails appear solid and substantial when photographed against the darkness of space. Yet, a human observer traveling through even the densest regions would encounter fewer molecules per cubic inch than exist in the best laboratory vacuums. The visual impression of substance results from the enormous volume of space occupied by the escaping particles, distributed across distances greater than the separation between Earth and Moon. The comet's dust tail follows the curved path of its orbit around the Sun, creating a broad fan of particles that spreads across millions of miles of space as different-sized grains follow slightly different trajectories according to their individual responses to radiation pressure and gravitational attraction. The mathematical description of this particle distribution, known as syndyne and synchrone analysis, allows astronomers to determine the timing and intensity of dust production events by tracking the orbital evolution of particles released at specific times during the comet's approach to the Sun. The ion tail, composed of electrically charged gases that glow through fluorescence as solar ultraviolet radiation excites their electrons to higher energy states, can extend more than 100 million miles from the nucleus when fully developed. This distance exceeds the orbital radius of Venus, meaning that a fully developed cometary ion tail could span the entire inner solar system if oriented favorably. The tail remains invisible to unaided human vision despite its enormous size because the excited gases emit light primarily in wavelengths outside the range of human color perception, requiring specialized filters and sensitive cameras to reveal the full extent of the structures. The development of both tails occurs according to physical processes that operate throughout the universe wherever small bodies approach close to stars, making comets natural laboratories for studying astrophysical phenomena that occur in other stellar systems. The same radiation pressure that shapes cometary tails also drives stellar winds from massive stars. While the magnetic interactions between ionized cometary gases and solar wind fields provide insights into the formation of planetary magnetospheres and the behavior of plasma in interstellar space, as the comet continues its approach toward the inner solar system, still months away from maximum activity, the gradual development of its tails provides astronomers with increasingly detailed information about the visitor's composition and internal structure. Spectroscopic analysis of the escaping gases reveals the presence of water vapor, carbon dioxide, carbon monoxide, methane, ammonia, and dozens of other molecular species, each contributing characteristic emission lines to the overall spectrum of light reflected and emitted by the expanding coma and developing tails. The comet's growing activity creates its own local environment in space, forming what planetary scientists call a comosphere, a region around the nucleus where escaping gases and dust particles interact with solar radiation and the solar wind according to the unique conditions created by the visitor's sublimation processes. This comosphere extends far beyond the visible coma, encompassing a volume of space larger than some planets, yet containing less total mass than a typical Earth-based mountain. The boundaries of this region remain invisible and constantly changing as solar wind conditions and the comet's gas production rates vary according to orbital position and surface heating patterns. The twin tails that emerge from this activity represent the visible manifestation of fundamental physical processes that have operated unchanged since the formation of planetary systems throughout the galaxy. The same radiation pressure, magnetic field interactions, and sublimation chemistry that create the comet's spectacular display also shaped the evolution of our solar system during its early epochs, when countless similar objects delivered water and organic compounds to the forming planets. The current visitor carries within its ancient structure a sample of the materials and processes that contributed to the chemical foundation for life on Earth, preserved in frozen form for billions of years, until solar heating unlocks these primordial components for scientific study. Beneath the glowing coma that now extends hundreds of thousands of miles from the comet's center lies the nucleus itself, a dark, irregularly shaped mountain of ice and rock that serves as the gravitational anchor for all the spectacular activity developing around it. This nucleus, perhaps 2 miles across at its widest dimension, spins slowly through space like a cosmic potato, its surface scarred by billions of years of micrometeorite impacts and shaped by the original accretion processes that assembled it from countless smaller particles in the protoplanetary disk of a distant star system. The visitor's low reflectivity makes it darker than charcoal, darker than the blackest volcanic glass found on Earth, absorbing solar energy with remarkable efficiency while revealing almost nothing of its detailed surface features to telescopic observation. High-resolution imaging attempts to penetrate the surrounding coma reveal tantalizingly brief glimpses of the nucleus itself, showing what appears to be an elongated object rotating with a period of approximately 18 hours. This rotation rate, neither particularly fast nor slow by cometry standards, suggests the nucleus formed through relatively gentle accretion processes rather than violent collisions that might have spun it faster or tidally locked its rotation to match its orbital period. The axis of rotation remains uncertain, hidden within the brightening coma. Yet infrared observations suggest that different regions of the surface experience varying amounts of solar heating during each rotation cycle, creating complex patterns of sublimation activity that change as the comet spins. The mystery of the nucleus's exact composition extends beyond the water ice and rocky materials detected through spectroscopic analysis of escaping gases. Theoretical models suggest the interior contains layers of different materials, deposited during distinct epochs of the comet's formation when the chemical composition of its birth nebula varied according to stellar winds, supernova explosions, and other events that enrich the interstellar medium with heavy elements. These layers, like pages in a cosmic history book, preserve isotopic signatures and molecular structures that encode information about galactic chemical evolution spanning millions of years before our solar system formed. The surface temperature of the illuminated hemisphere rises gradually as solar heating intensifies. Yet even at the comet's current distance from the Sun, the warmest regions barely exceed -150 degrees Fahrenheit, still cold enough to freeze carbon dioxide solid and maintain most organic compounds in crystalline form. The extreme temperature gradients between illuminated and shadowed regions create thermal stresses within the surface layers, potentially causing fractures and structural failures that could trigger sudden outbursts of sublimation activity when subsurface ice becomes exposed to direct solar radiation. Among the subtle ironies of cometry physics, the nucleus experiences its lowest temperatures not in the regions permanently shadowed from the Sun, but in areas where rapid sublimation removes heat faster than solar radiation can supply it. The phase transition from solid to gas requires significant amounts of energy, effectively cooling the surface through the same process that creates visible activity in the surrounding coma. This sublimation cooling can lower surface temperatures by tens of degrees below what simple radiative heating models would predict, creating complex thermal environments that vary according to the local composition and sublimation rates of different surface materials. The nucleus's extremely low density, estimated at perhaps half that of water ice, indicates a highly porous internal structure filled with voids, fractures, and loose aggregations of smaller particles rather than a solid mass of compressed ice and rock. This porosity, created during the original accretion process, when countless small particles stuck together under their mutual gravitational attraction, provides pathways for gases produced in the interior to migrate toward the surface, creating the complex patterns of jets and outbursts that characterize active cometry nuclei. The exact three-dimensional structure of these internal passages remains hidden from direct observation, yet influences every aspect of the comet's visible activity. Estimates of the nucleus's total mass, derived from observations of the orbital deflections experienced by particles in the surrounding coma, suggest the visitor contains approximately 10 billion tons of material, roughly equivalent to a terrestrial mountain, yet distributed across a volume much larger than any comparable earthly landform due to the porous internal structure. This mass represents an infinitesimal fraction of our solar system's total inventory, yet the nucleus carries within its structure samples of materials that formed under conditions no longer present anywhere in our galactic neighborhood, making it a priceless scientific treasure despite its modest size. The surface features visible through brief clearings in the coma suggest a landscape shaped by sublimation processes rather than the impact cratering and tectonic activity that dominate terrestrial planetary surfaces. Smooth plains alternate with rough, fractured terrain, possibly indicating regions where different types of ice sublimate at different rates under solar heating. The boundaries between these terrain types remain unclear due to the limited resolution of available observations. Yet they provide tantalizing hints about the internal structure and composition variations that create the complex patterns of activity observed in the surrounding coma. The nucleus maintains its structural integrity despite losing millions of tons of material each day through sublimation, demonstrating the remarkable mechanical properties of ice at extremely low temperatures and the binding effects of the organic compounds and rocky materials distributed throughout its matrix. Laboratory experiments suggest that ice at cometary temperatures becomes harder than many metals while retaining enough flexibility to accommodate thermal expansion and contraction without catastrophic structural failure. The organic compounds, similar to those found in carbonaceous meteorites, may serve as a kind of cosmic cement that helps hold the nucleus together during periods of intense sublimation activity. As solar heating continues to intensify during the comet's approach toward the inner solar system, the nucleus experiences increasing thermal stress as temperature gradients steepen and sublimation rates accelerate across its slowly rotating surface. The visitor's internal structure, preserved unchanged for billions of years in the cold of interstellar space, now faces its first significant challenge since formation as solar energy penetrates deeper into the surface layers and begins to mobilize volatile materials that have remained frozen since the era of galactic chemical evolution, when heavy elements were scarce and planetary systems were just beginning to form around the first generation of metal-rich stars. The dark nucleus continues its ancient rotation through space, carrying within its porous structure the chemical memory of stellar processes that operated when our galaxy was younger and less enriched with the elements necessary for rocky planets and organic chemistry. Each rotation exposes different regions to solar heating, creating complex cycles of warming and cooling that drive the spectacular displays visible in the surrounding coma, while gradually consuming the primordial materials that have traveled unchanged across millions of years and countless light years to reach our solar system during this brief period when human civilization possesses the technology necessary to study these ancient visitors from the depths of interstellar space. The light by which human observers study the comet carries within its photons a fundamental temporal displacement that separates observation from reality across the vast distances of interplanetary space. Solar radiation, traveling at precisely 186,282 miles per second through the vacuum between celestial objects, requires 8 minutes and 20 seconds to complete its journey from the Sun's photosphere to Earth's atmosphere, meaning that every telescopic observation of solar illumination reflects conditions that existed in the past rather than the present moment. When the comet resides at distances approaching the orbit of Jupiter, its reflected sunlight reaches Earth with delays exceeding 40 minutes, creating a temporal gap between the visitor's actual position and location and the images recorded by terrestrial cameras and spectrographs. This light travel delay becomes particularly significant as astronomers attempt to coordinate observations with specific phases of the comet's rotation cycle, or predict the exact timing of outbursts and other transient phenomena that characterize active cometary nuclei. Radio signals transmitted from Earth-based radar systems require even longer round-trip travel times to reach the comet and return with information about its surface features and internal structure, creating communication delays that challenge real-time studies of rapidly changing phenomena in the visitor's developing coma and tail structures. The photons that eventually reached terrestrial telescopes began their journey as nuclear fusion reactions in the Sun's core, where hydrogen nuclei combine under extreme temperature and pressure to create helium, releasing energy that slowly diffuses outward through the dense stellar interior over periods of hundreds of thousands of years. These fusion-generated photons undergo countless absorption and re-emission events as they migrate from the core toward the photosphere, gradually losing energy and increasing wavelength through this radiative diffusion process until they emerge as visible light and infrared radiation suitable for warming planetary surfaces and driving atmospheric circulation patterns. Once released from the Sun's surface, these photons travel unimpeded through the vacuum of interplanetary space until they encounter the comet's nucleus, where complex interactions between electromagnetic radiation and matter determine what fraction of the incident energy reflects back toward Earth in forms detectable by astronomical instruments. The comet's dark surface absorbs approximately 96% of the solar radiation that reaches it, converting this electromagnetic energy into thermal motion of surface molecules that drives sublimation processes and creates the expanding atmosphere of gases and dust particles surrounding the nucleus. The mystery of interpreting reflected and emitted radiation from the comet challenges astronomers because the observed light contains contributions from multiple physical processes occurring simultaneously across different regions of the nucleus and coma. Solar radiation reflected from the solid surface carries information about mineral composition and surface texture, while fluorescent emission from excited gases in the coma reveals the chemical composition of sublimating materials. Thermal emission at infrared wavelengths provides temperature measurements that help determine sublimation rates and internal heat conduction properties. Yet separating these various contributions requires sophisticated spectroscopic techniques and careful calibration of instrumental responses. Among the ironies of astronomical observation, the most detailed information about the comet's composition comes not from direct analysis of its solid nucleus, but from spectroscopic study of the gases and dust particles escaping from its surface through sublimation processes. These escaping materials, representing only a tiny fraction of the comet's total mass, provide chemical fingerprints that reveal the presence of water vapor, carbon dioxide, carbon monoxide, methane, ammonia, and dozens of other molecular species preserved in the nucleus since its formation billions of years ago. The relative abundances of these species, measured through the intensity of characteristic emission lines in the comet's spectrum, encode information about the temperature and chemical conditions present in the interstellar medium when the visitor first condensed from cosmic dust and gas. The light curves generated by photometric observations of the comet's brightness reveal periodic variations that correspond to its rotation period, as different regions of the irregularly shaped nucleus reflect varying amounts of sunlight during each 18-hour spin cycle. These brightness oscillations, typically amounting to several tenths of a magnitude over complete rotation cycles, provide indirect information about the nucleus's shape, surface features, and the distribution of active regions where sublimation processes create jets and outbursts of escaping gases. The mathematical analysis of these light curves requires careful separation of intrinsic brightness, variations caused by rotation, from the gradual overall brightening that occurs as the comet approaches closer to the Sun and sublimation activity intensifies. The polarization properties of reflected sunlight from the comet's coma and nucleus provide additional information about the size, distribution, and composition of dust particles suspended in the expanding atmosphere around the visitor. Solar radiation becomes partially polarized when it scatters from small particles, with the degree of polarization depending on particle size, composition, and the geometric relationship between the Sun, comet, and Earth during observation. These polarization measurements help distinguish between silicate and carbonaceous dust components and provide estimates of typical particle sizes in the coma. Information that contributes to understanding the original accretion processes that assembled the nucleus from smaller components in its birth stellar system. The Doppler shift of spectral lines emitted by gases in the comet's coma reveals the three-dimensional velocity structure of the expanding atmosphere, showing how escaping materials accelerate away from the nucleus under the combined influences of sublimation pressure, radiation pressure, and solar wind interactions. These velocity measurements, accurate to within a few meters per second despite the enormous distances involved, help map the flow patterns of gases as they escape from specific active regions on the nucleus surface and interact with the surrounding solar wind environment. The complexity of these velocity fields reflects the irregular shape of the nucleus and the non-uniform distribution of volatile materials across its surface. As the comet continues its approach toward maximum brightness, still months away from perihelion, the increasing intensity of reflected and emitted radiation provides astronomers with progressively more detailed information about this ancient visitor from interstellar space. Each photon that reaches terrestrial telescopes carries within its electromagnetic properties a message encoded by the physical and chemical processes occurring on and around the nucleus. Yet deciphering these messages requires sophisticated instruments and analysis techniques that push the limits of current observational capabilities. The light itself, traveling unchanged across millions of miles of vacuum, serves as the only messenger capable of bridging the enormous distances that separate human observers from this remnant of cosmic processes that operated billions of years before Earth formed its first solid crust or developed the atmospheric conditions necessary for liquid water to exist on its surface. The temporal displacement inherent in all astronomical observation means that every measurement of the comet's properties represents a glimpse into its past rather than its present state, creating a fundamental limitation on real-time studies of rapidly changing phenomena in the developing coma and tail structures. Yet this same light travel delay preserves information about the visitor's behavior across extended periods, allowing astronomers to construct time-lapse sequences that reveal the evolution of sublimation patterns and structural changes as solar heating gradually awakens the nucleus from its billion-year dormancy in the cold depths of interstellar space. At perihelion, the moment of closest approach to our star, the comet experiences thermal conditions unlike anything it has encountered during its millions of years wandering through interstellar space. Surface temperatures on the illuminated hemisphere rise to nearly 400 degrees Fahrenheit, hot enough to melt lead, hot enough to vaporize most organic compounds, yet still insufficient to penetrate more than a few meters into the nucleus's insulating interior, where primordial ice remains frozen at temperatures approaching absolute zero. This extreme temperature differential, spanning more than 600 degrees between surface and core, creates thermal gradients so steep that they challenge the structural integrity of materials that have remained stable for billions of years in the uniform cold of cosmic space. The intensity of solar radiation at perihelion exceeds by factors of hundreds the energy flux the comet received during its approach through the outer solar system, creating sublimation rates that can remove several meters of surface material during the brief weeks surrounding closest approach to the Sun. Water ice sublimates directly to vapor at rates measured in tons per second from each square kilometer of active surface, while more volatile compounds like carbon monoxide and methane escape even faster, creating pressure waves and shock fronts within the expanding coma as different gas species flow away from the nucleus at different velocities according to their molecular masses and thermal energies. The comet's orbital velocity reaches its maximum at perihelion, approaching speeds of 150,000 miles per hour as gravitational potential energy converts to kinetic motion according to the conservation laws that govern all celestial mechanics. At these velocities, the visitor crosses the diameter of Earth's orbit in less than 2 hours, moving so rapidly relative to our planet that telescopic tracking becomes challenging even for computer-controlled observatories equipped with sophisticated pointing systems. The combination of high orbital velocity and intense solar heating creates observational windows measured in days or weeks during which detailed studies must be completed before the comet recedes beyond the range of sensitive instruments. The mystery of predicting exactly when perihelion occurs illustrates the cumulative effects of small gravitational perturbations and non-gravitational forces that become significant only during the final months of the comet's approach to the Sun. Outgassing from the nucleus creates rocket-like effects as escaping gases carry momentum away from the surface, slightly altering the visitor's trajectory in ways that depend on the orientation of active regions relative to the direction of orbital motion. These non-gravitational accelerations, typically amounting to only millimeters per second squared, can shift the timing of perihelion by hours or days compared to predictions based purely on gravitational mechanics. Among the spectacular ironies of perihelion passage, the comet's closest approach to the Sun occurs at a distance still more than 30 times greater than the radius of our star's visible surface. Yet the visitor experiences radiation environments intense enough to drive off millions of tons of material per day. The inverse square law that governs radiative heating ensures that small changes in perihelion distance create dramatic differences in thermal stress and sublimation rates, making the exact geometry of closest approach crucial for determining whether the nucleus survives intact or fragments under thermal and tidal forces that exceed the weak gravitational self-attraction holding its components together. The tidal forces exerted by the Sun's gravity at perihelion stretch the comet along the line connecting its center to our star, creating differential accelerations between the near and far sides of the nucleus that amount to several times the visitor's own surface gravity. While these tidal stresses remain insufficient to disrupt a solid object of similar size, the comet's porous structure and weak internal cohesion make it vulnerable to fragmentation if pre-existing fractures or compositional boundaries create zones of structural weakness. Historical observations of previous comets suggest that perhaps 10% of sun-grazing visitors fragment during perihelion passage, creating spectacular displays as multiple components separate and develop independent coma and tail structures. The solar wind environment at perihelion differs dramatically from conditions in the outer solar system, with particle densities and magnetic field strengths elevated by factors of thousands compared to the relatively calm interplanetary medium through which the comet traveled during its approach. These intense plasma conditions create complex interactions between the visitor's escaping gases and the charged particle flows emanating from our star's corona, generating bow shocks, magnetic field draping, and other phenomena typically associated with planetary magnetospheres rather than small bodies in the solar system. The comet's ion tail reaches maximum development during perihelion passage as solar ultraviolet radiation ionizes escaping gases with unprecedented efficiency, creating glowing streamers of electrically charged particles that can extend more than 100 million miles behind the nucleus. These tail structures, visible to the naked eye from Earth when geometric conditions prove favorable, consist primarily of ionized water vapor, carbon dioxide, and other molecular species that fluoresce at specific wavelengths when excited by solar radiation. The tail's brightness and extent depend not only on the comet's gas production rate, but also on solar activity levels that can vary dramatically over periods of days or weeks as our star undergoes unpredictable changes in magnetic field configuration and coronal heating processes. The dust tail achieves its maximum breadth and complexity at perihelion as radiation pressure accelerates particles of all sizes away from the nucleus, creating curved streamers that trace the mathematical relationship between particle size, radiation pressure efficiency, and orbital mechanics. The largest dust grains, several millimeters in diameter, barely respond to radiation pressure and continue to follow orbits similar to the parent nucleus, while microscopic particles experience accelerations that quickly carry them away from the comet's vicinity at velocities exceeding the escape speed from our solar system. These size-dependent trajectories create the characteristic fan-shaped appearance of mature dust tails, with different regions dominated by particles released at different times during the comet's approach to perihelion. The brief weeks surrounding closest approach represent the culmination of the visitor's billion-year journey from the depths of interstellar space, transforming it from an invisible dark object into one of the most spectacular phenomena visible in Earth's sky. The ancient materials preserved within its nucleus experienced their first significant heating since formation, releasing water vapor and other compounds that have remained frozen since the era when our galaxy contained fewer heavy elements and stellar systems were less common than they are today. Each molecule that escapes carries with it isotopic signatures and chemical information that encode the conditions present in distant stellar regions during epochs that preceded the formation of our solar system by millions or billions of years. As the comet rounds perihelion and begins its journey back toward the outer solar system, it carries with it a slightly reduced mass and potentially altered internal structure. Having sacrificed some of its primordial material to create the spectacular displays that briefly illuminate our local region of space, the visitor's encounter with our star represents both an ending and a beginning, the conclusion of its approach phase and the start of its eventual return to the cold depths of interstellar space, where it will resume the patient wandering that characterizes most of its existence as it carries its remaining cargo of ancient materials toward future encounters with other stellar systems in the continuing dance of galactic dynamics that operates across timescales measured in millions of years. Past perihelion, the comet begins its long journey back toward the outer darkness of interstellar space, carrying with it a transformed appearance and slightly diminished mass after surrendering millions of tons of ancient material to create the spectacular displays that briefly illuminated our inner solar system. The visitor's orbital velocity gradually decreases as gravitational potential energy converts kinetic motion back into the stored energy of distance, following the same mathematical relationships that governed its inward approach, yet now operating in reverse as the sun's gravity works to slow rather than accelerate the escaping object. The dramatic tail structures that reached maximum development during closest approach now point away from the retreating sun, creating the counterintuitive appearance of a cosmic object fleeing from our star with its most prominent features trailing behind rather than leading its motion through space. The ion tail, composed of electrically charged gases that respond primarily to magnetic forces rather than gravitational attraction, maintains its orientation directly away from the sun regardless of the comet's orbital motion, creating spectacular geometric configurations as the visitor's path curves away from perihelion while its glowing tail continues to point radially outward from our star. This orientation effect, first explained through 19th century studies of electromagnetic radiation pressure, demonstrates how forces other than gravity can dominate the motion of matter in space when objects become sufficiently small or electrically charged to respond to radiation and magnetic field interactions. The dust tail follows more complex patterns determined by the orbital mechanics of individual particles released during different phases of the comet's approach and recession from the sun. Particles ejected during perihelion passage, when radiation pressure effects reached maximum intensity, follow hyperbolic trajectories that carry them permanently out of our solar system, while dust released during the early approach phase remains gravitationally bound and continues to orbit the sun in elliptical paths similar to those followed by asteroids and meteoroids. These different particle populations create layered structures within the dust tail that persist for months after perihelion, gradually spreading across millions of miles of space as orbital dynamics separate faster and slower moving components. The mystery of the comet's post-perihelion activity centers on the thermal inertia effects that cause maximum sublimation rates to occur several days or weeks after closest solar approach. Similar to the way terrestrial deserts reach peak temperatures in late afternoon rather than at solar noon, the nucleus's porous structure and poor thermal conductivity create significant delays between peak solar heating and maximum subsurface ice temperatures, resulting in gas production rates that continue to increase even as the comet recedes from the sun and solar flux begins to diminish. These thermal lag effects can maintain spectacular tail development for extended periods, sometimes creating the most impressive displays during the comet's outbound journey rather than during its approach to perihelion. Among the subtle ironies of post-perihelion dynamics, The comet's most dramatic changes in appearance occur during its retreat from the Sun rather than during its initial approach. As thermal energy stored within the nucleus during closest approach continues to drive sublimation processes at high rates even as solar heating diminishes according to the inverse square law, the visitor's coma can actually expand to maximum size weeks after perihelion. When delayed, thermal effects reach the nucleus interior and mobilize volatile materials that remained frozen during the rapid transit through the region of maximum solar heating. This temporal displacement between cause and effect demonstrates how the thermal properties of cosmic objects can create complex responses to changing external conditions. The comet's orbital trajectory beyond perihelion follows a hyperbolic path that gradually curves away from the Sun's gravitational influence, carrying the visitor toward an eventual escape velocity that will return it to interstellar space with a slightly different velocity vector than it possessed during its original approach to our solar system. The gravitational interactions with Jupiter, Saturn, and other massive planets that assisted its inward journey now operate in reverse, gradually removing orbital energy and deflecting the trajectory toward configurations that may determine which star system the comet approaches next during its continuing journey through galactic space. The visitor's post-perihelion velocity exceeds its approach velocity due to the gravitational acceleration gained during closest approach, following the same energy conservation principles that govern spacecraft trajectories and planetary orbital mechanics. This velocity increase, amounting to several kilometers per second, represents energy borrowed from the Sun's orbital motion around the galactic center, an infinitesimal change in our star's trajectory that demonstrates how gravitational interactions conserve momentum across all scales of cosmic motion, from binary asteroid systems to galactic encounters between massive stellar clusters. As the comet recedes beyond the orbit of Mars, then Earth, then Venus, the intensity of solar heating diminishes rapidly enough to begin freezing the escaping gases back onto the nucleus surface, creating complex frost patterns and surface modifications that preserve a record of the perihelion passage in crystalline structures that may persist for millions of years during the visitor's return to interstellar space. These freeze-back processes operate in reverse of the sublimation patterns that created the spectacular displays, gradually reducing the size and brightness of the coma and tail structures as thermal equilibrium shifts toward preservation rather than destruction of volatile materials. The dust particles that created the spectacular tail displays continue their independent journeys through interplanetary space long after the parent nucleus has receded beyond visibility, following elliptical and hyperbolic orbits that will eventually distribute ancient cometary material throughout our solar system. Some of these particles will intersect Earth's orbital path months or years later, creating meteor showers that connect terrestrial observers to the cosmic visitor through brief streaks of light as the ancient dust burns up in our planet's atmosphere at velocities approaching 70 kilometers per second. The comet's gradual fading occurs so slowly that human observers require months of careful measurement to detect the diminishing brightness and shrinking angular size of the coma and tail structures. Professional telescopes continue to track the visitor for years after perihelion, monitoring the decay of sublimation activity and the evolution of surface properties as solar heating becomes insufficient to maintain the spectacular displays that briefly transformed an invisible dark object into one of the most prominent features in Earth's sky. These extended observations provide crucial information about the long-term behavior of cometary nuclei and the durability of ancient materials under extreme thermal stress. The visitor's post-perihelion journey carries it through the same regions of space it traversed during approach. Yet, the thermal and chemical changes induced by solar heating have permanently altered its surface composition and internal structure. The nucleus now contains fractures, voids, and compositional modifications that did not exist during its inbound passage, creating a slightly different object that will respond differently to future encounters with stellar radiation should its trajectory eventually bring it close to another star system during its continuing galactic wanderings. As the comet crosses the orbit of Jupiter in its outbound journey, moving with the same stately patience that characterized its approach, yet now carrying within its structure the permanent modifications created by its brief encounter with intense solar heating. It begins the transition back towards the thermal equilibrium that will govern its existence during the next phase of interstellar travel. The visitor's spectacular displays gradually fade into memory, preserved in the photographic records and spectroscopic data gathered by human observers, while the nucleus itself resumes the dark anonymity that has characterized most of its existence since formation billions of years ago in the cold depths of cosmic space between the stars. The comet's recession beyond Saturn's orbital distance marks its gradual return to the thermal equilibrium that has governed its existence for billions of years. As solar heating becomes insufficient to maintain the spectacular sublimation processes that created its temporary transformation from dark wanderer to brilliant celestial spectacle. At this distance, roughly 9 astronomical units from our star, solar radiation provides barely 1% of the energy flux that illuminates Earth's surface, allowing the nucleus to begin the slow cooling process that will eventually restore surface temperatures approaching absolute zero during its journey back to interstellar space. The coma that once extended millions of miles from the visitor's center now contracts to a barely perceptible haze surrounding the nucleus, visible only through the most sensitive telescopic instruments equipped with specialized filters designed to detect the faint emission lines characteristic of residual gas production. The dust tail, no longer sustained by active sublimation from the nucleus surface, begins to disperse according to the complex gravitational and radiation pressure forces that govern the motion of small particles throughout the solar system. Individual dust grains continue to follow their own independent orbits around the Sun, gradually spreading across vast regions of interplanetary space as their slightly different orbital parameters cause faster-moving particles to separate from slower companions over periods of months and years. The largest particles, several centimeters in diameter, remain gravitationally bound to solar orbits that may eventually bring them close to the inner planets, while microscopic grains accelerated by radiation pressure to escape velocities contribute to the interplanetary dust population that fills the plane of our solar system. The ion tail, dependent on active gas production to maintain its glowing streamers of electrically charged particles, fades more rapidly than the dust structures as declining sublimation rates reduce the supply of neutral molecules available for ionization by solar ultraviolet radiation. The magnetic field interactions that once created dramatic tail disconnections and reconnection events during periods of variable solar wind conditions now operate on diminishing quantities of ionized material, gradually reducing the visitor's electromagnetic signature until it becomes indistinguishable from the background plasma environment of the outer solar system. The mystery of the comet's internal thermal state during this cooling phase challenges theoretical models that attempt to predict how deeply solar heating penetrated into the porous nucleus during perihelion passage and how long subsurface temperatures will remain elevated above their pre-encounter values. Computer simulations suggest that thermal energy absorbed during closest approach to the Sun may continue to drive low-level sublimation from internal ice deposits for decades after the surface has returned empty to its original frozen state, creating complex patterns of outgassing that could occasionally become visible through sensitive spectroscopic observations even when the comet appears inactive to conventional telescopic monitoring. Among the gradual transitions that characterize the comet's post-perihelion evolution, the visitor's surface undergoes chemical and physical modifications that permanently alter its reflectivity, thermal properties, and structural integrity compared to its original pristine state before solar encounter. Organic compounds heated above their decomposition temperatures during perihelion passage leave behind carbonaceous residues that darken the surface and change its thermal absorption characteristics. while the removal of volatile ices creates voids and fractures that increase porosity and reduce thermal conductivity throughout the outer layers of the nucleus. The comet's orbital velocity continues to decrease as gravitational potential energy replaces kinetic motion, following the mathematical relationships that govern all bound and unbound trajectories in gravitational fields throughout the universe. The visitor's current speed, while still impressive by terrestrial standards at approximately 50,000 miles per hour, represents only half the maximum velocity achieved during perihelion passage, demonstrating how orbital energy distributes between kinetic and potential components according to the visitor's instantaneous distance from the central gravitating body. The visitor's trajectory through this region of the outer solar system occurs during a period of relative gravitational calm, with minimal perturbations from the major planets whose orbital positions during the comet's outbound journey differ significantly from their configurations during its approach phase years earlier. These changed planetary alignments create slightly different gravitational influences that gradually modify the comet's path by small amounts, potentially altering its ultimate escape trajectory by degrees that could determine whether its next stellar encounter occurs in thousands or millions of years of future galactic travel. The comet's gradual fading from telescopic visibility occurs according to the inverse square law that governs both the illumination provided by solar radiation and the apparent brightness of objects observed from Earth. As the visitor's distance from the Sun doubles, the solar flux it receives decreases by a factor of 4, while its apparent brightness as viewed from Earth diminishes by factors that depend on both its increasing distance from the Sun and its growing separation from our planet's orbital position. These combined effects create brightness decline rates that can reduce the comet's visibility by several orders of magnitude within months of its passage beyond the orbit of Saturn. The nucleus rotation period, measured at approximately 18 hours during active phases when gas jets and outbursts provided clear markers for tracking rotational motion, may change slightly as the redistribution of mass caused by differential sublimation alters the visitor's moment of inertia and rotational dynamics. These spin rate modifications, typically small fractions of the original rotation period, preserve within the nucleus's motion a permanent record of the torques and asymmetric mass loss events that occurred during its encounter with intense solar heating at perihelion. As the comet continues its patient journey toward the gravitational boundary that separates our solar system from interstellar space, it carries within its modified structure a record of thermal and chemical processes that operated when our star was briefly the dominant influence on its evolution after millions of years of unchanging conditions during interstellar travel. The surface fractures, internal void networks, and chemical alterations created by solar heating will persist throughout the visitor's eventual return to cosmic darkness, serving as permanent markers of its temporary membership in our planetary system during the brief epoch when human civilization possessed sufficient technological capability to observe and study these ancient messengers from the depths of galactic space. The visitor's approach to gravitational escape occurs so gradually that the mathematical moment when it crosses the boundary between bound and unbound motion remains difficult to determine precisely. Dependent on subtle perturbations from distant planets and the cumulative effects of non-gravitational forces that become significant only when integrated over extended time periods, the comet's eventual departure from our solar system will occur as gently as its original arrival, marked not by dramatic acceleration or sudden trajectory changes, but by the slow accumulation of gravitational potential energy until the visitor achieves sufficient total energy to overcome the Sun's gravitational attraction and resume its journey through the vast emptiness that separates stellar systems throughout our galaxy. The mathematical moment of gravitational escape occurs without fanfare or visible indication, marked only by the abstract crossing of an energy threshold that transforms the comet from a temporary visitor to our solar system into a permanent exile returning to interstellar space. This transition from bound to unbound trajectory happens gradually over periods of months as the visitor's total energy, the sum of kinetic motion and gravitational potential relative to our Sun, slowly increases beyond the zero value that separates elliptical orbits from hyperbolic escape paths. The precise instant of escape remains impossible to determine through observation, buried within the uncertainties of orbital calculations that must account for gravitational perturbations from dozens of solar system objects and the cumulative effects of non-gravitational forces too small to measure directly, yet significant when integrated across astronomical timescales. The comet's escape velocity, achieved through the gravitational acceleration gained during its passage through the inner solar system, exceeds by several kilometers per second the minimum speed required to overcome solar gravity at its current distance from our star. This excess velocity, borrowed from the orbital energy of the planetary system through gravitational interactions that operate according to the strict conservation laws governing all mechanical systems, will carry the visitor through interstellar space at speeds sufficient to traverse the distance between neighboring stars in less than 100,000 years. Brief intervals by galactic standards, yet encompassing thousands of human generations. The visitor's new trajectory, altered by the gravitational influences of Jupiter, Saturn, and our Sun during its passage through the planetary region, points toward a different region of galactic space than the direction from which it originally approached our solar system. This deflection, amounting to several degrees of arc when measured against the background stars, represents a permanent change in the comet's path through the galaxy that will determine which stellar systems it encounters during future epochs of galactic evolution. The mathematical prediction of these future encounters requires knowledge of stellar motions and gravitational influences that remain uncertain beyond time horizons of several million years, making the visitor's ultimate fate impossible to determine with precision. The comet's orbital period around the galactic center, inherited from its previous stellar associations and modified by its encounter with our solar system, spans approximately 200 million years. The time required for objects at our distance from the galactic nucleus to complete one revolution around the central black hole, whose gravitational influence organizes the motion of hundreds of billions of stars into the spiral structure visible in other galaxies throughout the universe. During this galactic year, the visitor will encounter changing gravitational environments as it passes through spiral arms, stellar associations, and regions of varying matter density that characterize different zones of our galaxy's complex structure. The mystery of the comet's future evolution during its return to interstellar travel centers on the gradual effects of cosmic ray bombardment, micrometeorite impacts, and gravitational perturbations from passing stars that will slowly modify its surface composition, internal structure, and orbital characteristics over millions of years of solitary wandering through cosmic space. These processes operate at rates so slow that they require geological timescales to produce measurable changes. Yet their cumulative effects over millions of orbital periods around the galaxy may completely alter the visitor's physical properties long before it encounters another stellar system capable of providing the thermal energy necessary to reactivate sublimation processes. Among the patient ironies of galactic dynamics, the comet's escape from our solar system occurs during a period when our Sun occupies a relatively quiet region of the galaxy's spiral structure, far from the massive star-forming regions and supernova remnants that create turbulent gravitational and radiation environments capable of dramatically altering the trajectories of small interstellar objects. Had the visitor's arrival coincided with our solar system's passage through a spiral arm or stellar association, its encounter with our Sun might have been complicated by gravitational influences from nearby massive stars, potentially altering its trajectory enough to prevent escape or deflect it toward dramatically different future destinations within the galaxy. The visitor's journey through the outer reaches of our solar system occurs in a region where solar gravity gradually diminishes until it becomes comparable to the gravitational influences of nearby stars, creating a complex transition zone where multiple stellar systems compete for gravitational dominance over small objects traveling at interstellar velocities. The heliopause, where solar wind meets interstellar medium, marks one boundary of this transition region, while the gravitational sphere of influence extends much farther into space, encompassing volumes larger than entire planetary systems, yet containing gravitational fields too weak to significantly deflect objects moving at cosmic velocities. The comet's thermal evolution during its escape phase follows predictable patterns as solar heating becomes insufficient to maintain surface temperatures above the sublimation points of even the most volatile compounds preserved within its nucleus. Carbon monoxide, methane, and other trace gases that created spectral signatures during the visitor's active phase gradually freeze back onto internal surfaces, restoring chemical equilibrium conditions that have characterized most of the comet's existence since its formation in the interstellar medium billions of years ago. These freeze-back processes occur slowly enough that residual outgassing may continue for decades after the nucleus appears completely inactive to telescopic observation. The visitor's gradual transition from visible object to invisible wanderer occurs according to the same physical principles that govern the detectability of all astronomical objects, dependent on the balance between intrinsic brightness, distance from observers, and the sensitivity limits of available instruments. Professional telescopes equipped with sensitive cameras and specialized filters continue to track the fading comet for years after it becomes invisible to smaller instruments, monitoring its brightness decline and searching for evidence of residual activity that might indicate ongoing sublimation processes or structural changes resulting from thermal stress experienced during perihelion passage. As the comet crosses the orbital distance of Neptune in its outbound journey, moving with the same stately patience that characterized its approach, yet now carrying within its structure permanent modifications created by solar heating, it begins the final phase of its departure from our stellar neighborhood. The visitor's surface bears the scars of thermal stress, chemical alteration, and mass loss that distinguish it from the pristine object that first entered our solar system years earlier. Yet these changes represent only superficial modifications to a bulk composition and internal structure that remain fundamentally unchanged since the epoch of its formation in cosmic space between distant stars. The nuclear processes that power our Sun continue their steady conversion of hydrogen to helium, generating the radiation pressure and gravitational fields that accelerated the visitor through its spectacular transformation from dark wanderer to brilliant comet and back to invisible exile. Yet, these stellar processes operate on timescales so vast that they remain essentially constant throughout the brief intervals required for cometary encounters. The comet's entire passage through our solar system, from first gravitational detection to final escape beyond planetary influence, represents less than 1/10,000,000th of our Sun's total lifetime, demonstrating how the rhythm of cosmic encounters operates according to timescales that dwarf human experience, yet remain brief episodes in the context of stellar evolution and galactic dynamics. Deep time flows around the comet's trajectory like an invisible river, carrying all matter through the universe, according to rhythms that predate the formation of galaxies and will continue long after the last stars exhaust their nuclear fuel and fade into cosmic darkness. The visitor's current journey represents only the latest chapter in a story that began billions of years ago when gravitational collapse within a molecular cloud first assembled the ice and rock components that form its nucleus. Preserving within that ancient structure chemical signatures of stellar processes that operated when our galaxy contained fewer heavy elements and planetary systems remained rare exceptions rather than common features of stellar evolution. Each molecule of water, each grain of cosmic dust, each trace of organic compounds locked within the comet's interior carries isotopic fingerprints that connect its current trajectory through our solar system to specific epochs of galactic chemical evolution spanning millions of years before our Sun ignited its nuclear fires. The comet has likely completed this same orbital dance around distant stars countless times during its wandering through interstellar space, experiencing similar cycles of approach, heating, sublimation, and recession as it encountered other stellar systems during its journey through different regions of the galaxy's spiral structure. Each previous encounter left subtle modifications in its surface composition, internal structure, and orbital characteristics, gradually transforming the visitor from its original pristine state into the complex object that human observers now study through telescopic analysis of its reflected light and escaping gases. These accumulated changes preserve within the nucleus a layered record of stellar encounters that extends back through galactic time to the era when heavy elements first became abundant enough to support the formation of rocky planets and complex chemistry. The mathematical description of the comet's orbit around our Sun follows the same gravitational principles that govern the motion of planets, moons, asteroids, and artificial satellites throughout the universe. Yet, its hyperbolic trajectory distinguishes it from the permanently bound objects that constitute our solar system's stable population. This mathematical distinction between elliptical and hyperbolic paths represents a fundamental division in celestial mechanics between objects that belong to specific stellar systems and those that wander freely through galactic space, carrying materials and information between stellar neighborhoods according to the gravitational dynamics that organize matter on the largest astronomical scales. The precise orbital elements that characterize the comet's path through space, its semi-major axis, eccentricity, inclination, and angular parameters encode within their numerical values the gravitational history of every stellar encounter the visitor has experienced during its galactic travels. These orbital characteristics serve as a kind of cosmic memory that preserves information about gravitational interactions spanning millions of years. Though the chaotic nature of multi-body gravitational systems ensures that this information becomes increasingly uncertain as astronomers attempt to trace the visitor's trajectory backward through time beyond horizons measured in thousands of orbital periods around the galactic center. The mystery of the comet's original formation environment deepens as spectroscopic analysis reveals isotopic ratios and molecular compositions that suggest assembly in stellar regions with different chemical characteristics than those present in our local galactic neighborhood today. The abundance of heavy water relative to normal water, the ratio of carbon isotopes, and the presence of rare molecular species indicate formation in interstellar environments enriched by specific types of stellar explosions and mass ejection events that may no longer occur in regions of the galaxy where star formation has progressed beyond the initial phases of heavy element production that characterized our cosmic vicinity billions of years ago. Among the profound ironies of cosmic evolution, the comet's brief visibility during its passage through our solar system provides human observers with direct access to materials and chemical processes that operated during epochs of galactic history that remain otherwise inaccessible to scientific study. The visitor serves as a natural time capsule that has preserved samples of the interstellar medium from eras when our galaxy was younger, less chemically evolved, and organized according to different patterns of stellar formation and galactic structure. These ancient materials, locked in frozen preservation during millions of years of interstellar travel, become available for analysis only during the brief periods when solar heating sublimes surface ices and releases gases that carry isotopic and molecular signatures of cosmic processes that occurred long before our solar system formed. The comet's rotation period of approximately 18 hours, inherited from the gravitational torques and angular momentum exchanges that occurred during its formation and subsequent stellar encounters, will persist essentially unchanged throughout its future galactic travels, unless modified by catastrophic events like close approaches to massive stars or collisions with other interstellar objects. This rotational motion preserves within its angular momentum a record of the dynamical processes that shaped the visitor's structure during its assembly from smaller components. Maintaining this mechanical memory across timescales that encompass the evolution of entire stellar populations and the chemical enrichment of galactic regions through successive generations of stellar formation and explosion. The visitor's structural integrity, maintained despite losing significant mass during perihelion passage and experiencing thermal stresses that exceeded anything encountered during its interstellar journey, demonstrates the remarkable mechanical properties of materials that formed under the extreme conditions present in molecular clouds during the early phases of stellar system formation. The organic compounds and silicate grains that serve as binding agents within the ice matrix exhibit strength and durability characteristics that reflect their origins in environments where temperature, pressure, and radiation conditions differ dramatically from those present in contemporary star-forming regions where planetary systems currently develop around newly formed stars. The comet's future trajectory through interstellar space will carry it through regions of the galaxy that may differ significantly in matter density, radiation environment, and gravitational field structure from the cosmic neighborhood where it spent the previous millions of years before approaching our solar system. These changing galactic environments will subject the visitor to different rates of cosmic ray bombardment, interstellar dust erosion, and gravitational perturbation that gradually modify its surface properties and orbital characteristics according to processes that operate so slowly that their effects become apparent only over timescales measured in millions of years. As the comet continues its recession beyond the gravitational influence of our planetary system, carrying within its ancient structure the chemical memories of cosmic processes that operated before Earth, developed oceans or atmospheres capable of supporting complex chemistry. It resumes the patient wandering that has characterized most of its existence since condensation from the primordial molecular cloud that gave birth to its parent stellar system. The visitor's brief illumination in our sky represents a fleeting moment in a story that spans galactic time, connecting human observers to cosmic processes that operated across distances and durations that challenge comprehension yet remain accessible through the mathematical language of physics and the patient analysis of light reflected from ancient ice preserved in the darkness between stars. The deep time that governs the comet's existence operates according to rhythms that encompass the formation and destruction of stellar systems, the chemical evolution of galactic regions, and the slow gravitational dance that organizes matter across cosmic distances. Yet this vast temporal framework remains connected to human observation through the universal physical laws that govern the behavior of matter and energy at all scales of space and time throughout the observable universe. Among the billions of similar objects that drift through the cold emptiness between stellar systems throughout our galaxy, the comet designated 3Y/Atlas represents but one voice in a vast, slow symphony of cosmic motion that operates according to gravitational mathematics, unchanged since the universe first cooled enough for matter to condense into discrete objects capable of maintaining structural integrity across astronomical timescales. Countless other visitors wander through interstellar space along trajectories that may eventually bring them into the gravitational influence of distant stars, each carrying within its frozen nucleus samples of the chemical conditions present during different epochs of galactic evolution, when heavy elements possessed different abundances and stellar formation proceeded according to patterns that have since evolved beyond recognition. The statistical probability of detecting interstellar comets entering our solar system depends on factors that include their intrinsic numbers in galactic space, their size distribution, the geometric likelihood of gravitational capture by our sun's influence, and the sensitivity limits of terrestrial observation systems capable of distinguishing these visitors from the much more numerous population of objects that originated within our own planetary system. Current estimates suggest that perhaps one interstellar comet enters the inner solar system each year, though most remain too small or approach too distant from Earth's orbital position to achieve the brightness necessary for detection by existing telescopic surveys designed primarily to catalog asteroids and comets that pose potential impact hazards to our planet. The visitor's relatively large size and favorable orbital geometry, which brought it within telescopic range during a period when sophisticated instruments were available to study its composition and behavior, represents a fortunate coincidence that may not recur for decades or centuries, depending on the random arrival patterns of similar objects from interstellar space. The scientific opportunity presented by 3I/Atlas, direct observation and analysis of materials preserved since the formation of distant stellar systems, illustrates how astronomical research often depends on unpredictable events that provide brief windows for gathering information about cosmic processes that remain otherwise inaccessible to human investigation. The comet's chemical composition, revealed through spectroscopic analysis of gases escaping from its nucleus during active phases of sublimation, shows both similarities and differences compared to comets that formed within our own solar system during the early phases of planetary accretion around our young sun. The presence of water vapor, carbon dioxide, carbon monoxide, and organic compounds matches expectations based on theoretical models of molecular cloud chemistry. Yet the precise isotopic ratios and trace element abundances indicate formation under conditions that differed subtly from those present in the protoplanetary disk, where Earth and the other planets assembled from dust and gas gravitationally bound to our star. The mystery of determining how many stellar systems the comet has encountered during its galactic wanderings challenges astronomers because each gravitational interaction with massive objects gradually erases evidence of previous orbital history through the cumulative effects of chaotic dynamics that make long-term trajectory prediction impossible beyond certain temporal horizons. Computer simulations suggest that typical interstellar objects experience close approaches to stars perhaps once every few million years, implying that 3I/Atlas may have visited dozens or hundreds of stellar systems during its journey through different regions of galactic space, each encounter leaving subtle modifications in its velocity vector and internal structure. Among the profound implications of studying interstellar visitors like 3I/Atlas, these objects provide direct access to the inventory of materials and chemical processes that characterize regions of the galaxy beyond our immediate stellar neighborhood, offering insights into the diversity of planetary formation environments and the range of conditions under which complex chemistry can develop around different types of stars. The isotopic signatures preserved within cometary nuclei serve as natural samples of interstellar medium composition from locations and epochs that remain inaccessible to other forms of astronomical observation, creating opportunities for comparative planetology that extends beyond our solar system to encompass galactic-scale chemical evolution. The comet's brief active period during its passage through our inner solar system represents a natural experiment in the physics and chemistry of sublimation processes operating under well-characterized environmental conditions, providing detailed observations of how ancient materials respond to thermal stress after billions of years of preservation at temperatures approaching absolute zero. These observations contribute to understanding the fundamental properties of ices, organic compounds, and mineral components that formed during early phases of stellar evolution when the universe was younger and chemically simpler than contemporary star-forming regions where planetary systems currently develop around newly ignited protostars. The visitor's trajectory through our solar system, determined by gravitational interactions that operate according to mathematical principles discovered centuries ago, yet applied to objects whose origins span galactic distances and cosmic timescales, demonstrates the universal applicability of physical laws that govern the behavior of matter and energy throughout the observable universe. The same equations that describe planetary motion around our Sun accurately predict the comet's hyperbolic path through interplanetary space, illustrating how local physical principles extend to cosmic phenomena that involve materials and processes from distant stellar systems. The dust particles released from the comet's nucleus during active sublimation phases will continue to orbit through our solar system for millions of years after the parent object has returned to interstellar space, gradually spreading throughout the planetary region and contributing microscopic samples of ancient materials to the zodiacal dust cloud that fills the plane of our solar system. Some of these particles may eventually intersect Earth's orbital path, creating meteor displays that connect terrestrial observers to cosmic processes that operated in distant stellar systems billions of years before our planet developed the atmospheric and geological conditions necessary for complex chemistry and biological evolution. The mathematical description of the comet's orbit, expressed through the classical formalism of celestial mechanics, yet applied to an object that carries chemical information from regions of galactic space separated from our location by thousands of light years and millions of years of travel time, bridges the conceptual gap between local astronomical phenomena and cosmic processes that operate on scales encompassing entire spiral arms of galactic structure. The visitor's presence in our sky during this brief historical moment, when human civilization possesses sufficient technological capability to study its composition and behavior, represents a convergence of cosmic coincidences that may not recur for many generations. As 3I/Atlas continues its recession toward the boundary between our solar system and interstellar space, it carries with it permanent modifications in surface composition and internal structure created by its encounter with solar radiation, serving as a messenger that will transport information about our star's thermal and gravitational environment to whatever stellar systems it encounters during future epochs of galactic evolution. The comet's brief membership in our planetary family leaves traces in the chemical composition of our solar system's dust inventory, while taking with it samples of solar wind particles and photochemical products that encode information about our sun's current activity levels and magnetic field characteristics. The visitor's return to the darkness between stars occurs with the same unhurried patience that characterized every phase of its journey through our solar system, following gravitational mathematics that operate according to timescales measured in millions of years rather than human generations, yet governed by physical principles that remain constant throughout the universe's vast temporal and spatial domains. As 3I/Atlas crosses the invisible boundary that separates our sun's gravitational influence from the general galactic environment, it resumes the interstellar wandering that has defined most of its existence since formation in cosmic space around a distant star whose light may no longer shine in the same region of galactic space where the comet first condensed from molecular cloud materials billions of years ago. The comet's escape velocity, gained through gravitational acceleration during its passage through the inner solar system, will carry it through interstellar space at approximately 26 kilometers per second relative to our local stellar rest frame, sufficient speed to traverse the typical distances between neighboring stars in less than 50,000 years, though the visitor's trajectory points toward regions of galactic space where stellar densities remain lower than average and the next close stellar encounter may not occur for hundreds of thousands of years. This velocity represents energy borrowed from our solar system's orbital motion around the galactic center, an infinitesimal change in our star's trajectory that demonstrates how gravitational interactions redistribute momentum across astronomical scales according to conservation laws that operate from subatomic particles to galactic clusters. The thermal equilibrium that will govern the comet's existence during its return to interstellar travel approaches the cosmic background temperature of approximately 3 degrees above absolute zero, the residual thermal radiation left over from the universe's formation that provides a uniform energy source throughout cosmic space, insufficient to drive chemical reactions or phase transitions, yet serving as a baseline temperature that prevents matter from reaching absolute zero even in the emptiest regions between galactic superclusters. The visitor's surface temperature will gradually approach this cosmic equilibrium over periods of thousands of years, as stored thermal energy from solar heating slowly radiates away into the infinite heat sink of expanding space. The mystery of the comet's ultimate fate during future galactic travels depends on the statistical likelihood of encountering massive objects capable of significantly altering its trajectory or internal structure through gravitational interactions, stellar radiation, or direct collisions with other interstellar materials. Computer simulations suggest that typical interstellar objects experience close approaches to main sequence stars perhaps once every few million years. Encounters with stellar remnants like white dwarfs or neutron stars on longer time scales, and possible gravitational interactions with massive molecular clouds or stellar associations that could dramatically modify orbital characteristics over periods encompassing multiple galactic rotations. Among the patient ironies of cosmic evolution, the comet's brief illumination during its passage through our solar system may represent the most dramatic period of its entire existence since formation. Yet, this spectacular transformation from invisible wanderer to brilliant celestial display occupies less than 1% of the time required for a single orbit around the galactic center. The visitor spends the vast majority of its existence in cold, dark anonymity, preserving ancient materials in perfect frozen storage while wandering through regions of space where stellar densities remain too low to provide the gravitational and thermal influences necessary to reactivate sublimation processes that reveal its chemical composition to potential observers. The comet's chemical inventory, slightly depleted by mass loss during perihelion passage, yet fundamentally unchanged in its basic composition and isotopic characteristics, will continue to preserve samples of interstellar medium chemistry from the epoch of its formation throughout future encounters with stellar systems that may possess dramatically different characteristics than our own sun and planetary family. The visitor serves as a natural probe carrying information between stellar neighborhoods separated by vast distances and time scales, potentially delivering chemical signatures of our solar system's environment to observers in distant stellar systems millions of years in the future. The visitor's trajectory through galactic space will be gradually modified by gravitational interactions with passing stars, molecular clouds, and other massive objects according to the same chaotic dynamics that have shaped its path through cosmic space since its original ejection from its birth stellar system. These accumulated perturbations ensure that the comet's future encounters with stellar systems remain fundamentally unpredictable beyond time horizons of several million years. Yet the statistical properties of galactic dynamics suggest that it will eventually approach other stars closely enough to experience thermal environments similar to those it encountered during its passage through our solar system. The organic compounds and silicate minerals that serve as binding agents within the comet's ice matrix will continue to undergo slow chemical modifications due to cosmic ray bombardment, radiative processing by background starlight, and gradual structural changes caused by thermal cycling during stellar encounters that occur over astronomical timescales. These processes operate so slowly that they require millions of years to produce measurable alterations in bulk composition. Yet, their cumulative effects over multiple galactic orbits may eventually transform the visitor's chemical properties beyond recognition compared to its current state as it departs our solar system. The mathematical framework that describes the comet's motion through galactic space encompasses gravitational interactions with hundreds of billions of stars, gas clouds, and other massive objects that constitute our galaxy's total mass inventory. Yet the complexity of this many-body gravitational system ensures that long-term predictions become increasingly uncertain as time horizons extend beyond the orbital periods of local stellar groups and spiral arm rotation patterns. The visitor's path through this gravitational landscape follows deterministic physical laws that remain perfectly understood in principle, yet practically impossible to integrate over the vast timescales that characterize galactic dynamics. As 3I/Atlas fades beyond the detection limits of terrestrial telescopes, becoming once again an invisible wanderer carrying its cargo of ancient materials through the patient darkness of interstellar space, it leaves behind in our solar system's dust inventory microscopic samples of interstellar chemistry that will persist for millions of years as permanent traces of its brief visit to our cosmic neighborhood. These dust particles, gradually dispersing throughout the planetary region according to radiation pressure and gravitational influences, serve as lasting connections between our solar system and the distant stellar regions where the comet originated billions of years ago. The visitor's departure marks the end of a scientific opportunity that may not recur for decades or centuries. Depending on the random arrival patterns of similar objects from interstellar space and the development of observational technologies capable of detecting and studying these ancient messengers from distant stellar systems. The knowledge gained from telescopic analysis of 3I/Atlas, direct measurements of interstellar medium chemistry, isotopic signatures of distant stellar nucleosynthesis, and observations of sublimation processes operating on materials preserved since galactic antiquity, contributes to understanding cosmic chemical evolution and planetary formation processes that extend far beyond our local stellar neighborhood to encompass the diversity of environments where complex chemistry develops around different types of stars throughout our galaxy's spiral structure. The comet's return to interstellar darkness occurs during a period when our solar system occupies a relatively quiet region of galactic space, far from the massive star-forming complexes and supernova remnants that create turbulent radiation and gravitational environments capable of dramatically altering the trajectories and compositions of small interstellar objects. The visitor's peaceful departure from our cosmic vicinity reflects the current stability of our local galactic environment, though this tranquil period represents only a brief phase in the ongoing cycle of stellar formation, evolution, and death that continuously reshapes the gravitational and chemical landscape through which interstellar wanderers like 3I/Atlas navigate during their eternal journeys through cosmic space. The physical processes that govern the comet's transformation from dark wanderer to spectacular celestial display and back to invisible exile operate according to universal principles that remain constant throughout space and time, yet manifest differently around each star system depending on stellar mass, luminosity, planetary configuration, and the countless other variables that determine local environmental conditions. The visitor's experience in our solar system provides one example of how interstellar materials respond to stellar heating, but similar objects approaching different types of stars would undergo variations in sublimation chemistry, tail development, and structural modification that reflect the enormous diversity of stellar environments present throughout our galaxy's population of hundreds of billions of stars. The comet's gradual recession beyond our sun's gravitational sphere of influence marks its transition from temporary solar system member back to permanent galactic citizen, carrying within its modified structure a record of thermal and chemical processes that operated during its brief encounter with our star's radiation environment. This stored information, encoded in surface fractures, internal void networks, and compositional modifications created by solar heating, will persist throughout the visitor's future interstellar travels, serving as a permanent marker of its temporary association with our planetary system during the current epoch of cosmic history, when human civilization possesses sufficient technological capability to observe and study these messengers from distant stellar regions. The silence that accompanies the comet's departure into interstellar space represents not absence, but the return to equilibrium conditions that have characterized most of its existence since formation. The profound quiet of cosmic vacuum where sound cannot propagate, where thermal energy flows according to radiation laws rather than convection or conduction, and where matter moves according to gravitational mathematics that operate with perfect precision across distances and timescales that dwarf human comprehension yet remain accessible through the universal language of physics that connects local observations to cosmic phenomena spanning galactic distances and geological time periods. As 3I/Atlas continues its patient journey toward whatever stellar encounters await in the distant future, it carries within its ancient nucleus the chemical memory of cosmic processes that operated before our solar system existed. Preserving these primordial materials in perfect frozen storage while wandering through the vast emptiness that separates stellar systems according to the same gravitational dynamics that organize matter on all scales throughout the observable universe, the visitor's brief visibility in our sky represents a fleeting connection between human observers and cosmic evolution spanning billions of years, demonstrating how the patient investigation of reflected starlight can reveal the chemical history of distant stellar regions and the physical processes that govern galaxy formation during epochs when the universe was younger and less chemically complex than the cosmic environment where planetary systems currently develop around newly formed stars throughout our galactic neighborhood. In the deepest cold of space, far from any star, countless similar objects drift in patient orbits through the darkness between worlds, carrying their cargo of ancient materials through gravitational fields so weak that centuries pass between measurable changes in velocity or direction. The universe expands around them according to cosmological mathematics that operate on scales encompassing billions of galaxies. Yet, these wandering mountains of ice and rock maintain their structural integrity across time periods that span the formation and dissolution of entire stellar populations. The silence that governs interstellar space extends beyond the mere absence of atmospheric molecules capable of carrying sound waves, encompassing a profound stillness where thermal motion slows to quantum mechanical minimums and chemical reactions cease entirely except for the rarest interactions between cosmic ray particles and atomic nuclei embedded in frozen matrices that have remained undisturbed since the epoch of galactic chemical evolution, when heavy elements first became abundant enough to support complex molecular chemistry. Each wandering comet preserves within its nucleus samples of the cosmic conditions present during different phases of stellar formation and galactic structure evolution, serving as natural time capsules that carry information across distances and durations that challenge human comprehension yet remain connected to terrestrial observation through the universal physical laws that govern the behavior of matter and energy throughout space and time. The mathematical relationships that describe orbital motion, thermal equilibrium, and chemical preservation operate with identical precision whether applied to objects in our immediate solar system vicinity or to materials that originated around stars separated from our location by thousands of light years and millions of years of travel through the patient darkness. The cosmic background radiation that permeates all space provides a gentle thermal foundation that prevents temperatures from reaching absolute zero even in the emptiest regions between galactic superclusters, maintaining conditions where quantum mechanical processes continue to operate according to probability distributions that preserve the fundamental properties of matter across astronomical timescales. This residual energy from the universe's formation ensures that frozen materials retain their molecular structure and chemical information indefinitely, creating natural archives of cosmic evolution that remain accessible to scientific investigation whenever stellar encounters provide sufficient thermal energy to sublimate surface layers and release gases that carry isotopic signatures of distant stellar nucleosynthesis processes. The galactic rotation that carries our solar system through different regions of stellar density and chemical composition operates so slowly that millions of human generations pass between significant changes in our cosmic environment. Yet this motion ensures that interstellar wanderers like comets eventually encounter the gravitational and thermal influences necessary to reveal their ancient secrets to potential observers equipped with instruments capable of analyzing reflected starlight and sublimation products. The convergence of cosmic timing that brings these messengers from distant stellar regions into telescopic range during periods when technological civilization possesses sufficient capability for detailed study represents a form of cosmic serendipity that connects human curiosity to the deepest mysteries of galactic evolution and stellar formation processes that operated long before our planet developed the atmospheric and geological conditions necessary for complex chemistry and biological development. In this vast, patient darkness, time flows according to rhythms that encompass the birth and death of stars, the formation and destruction of planetary systems, and the slow chemical enrichment of galactic regions through successive generations of stellar nucleosynthesis. Yet these cosmic processes remain governed by physical principles that operate with mathematical precision throughout the observable universe, creating connections between local phenomena and cosmic evolution that extend across scales of space and time that surpass imagination, yet remain accessible through the patient analysis of light, reflected from ancient ice preserved in the silence between stars, where countless similar visitors continue their eternal journeys through the expanding universe, carrying their secrets through the cosmic night toward future encounters that may reveal their ancient stories to civilizations not yet born, around stars not yet formed in regions of galactic space where heavy elements continue to accumulate through stellar processes that operate according to nuclear physics, unchanged since the universe first cooled enough for matter to condense into discrete objects capable of preserving chemical information across the vast temporal and spatial scales that characterize cosmic evolution in an expanding universe where distances grow larger and temperatures grow colder with each passing epoch. Yet, where the fundamental laws of physics ensure that matter and energy continue to interact according to mathematical relationships that remain constant throughout space and time, connecting every observation of reflected starlight to the deepest principles that govern the behavior of the cosmos itself.